Why transformers are rated in kVA instead of kW? Transformers are foundational components in electrical power systems, playing a vital role in stepping voltage levels up or down to ensure safe and efficient power distribution. While most electrical devices, such as motors and heaters, are rated in kilowatts, kW, transformers are uniquely rated in kilovolt-amperes, kVA. This difference might seem technical, but it has a practical and engineering rationale rooted in how electrical power behaves and how transformers handle energy internally. To appreciate this distinction, it's essential to understand the two types of electrical power, apparent power and real power. Apparent power, measured in kVA, represents the total power flowing through a circuit, without accounting for any phase difference between voltage and current. It combines both the useful power and the power lost due to system inefficiencies. Real power, measured in kW, is the actual usable power that performs the work like turning a motor or lighting a bulb. The relationship between these two types of power is defined by the power factor, PF, which is the ratio of real power to apparent power. kW is equal to kVA times PF. The power factor can vary depending on the nature of the load. Purely resistive loads have a power factor of 1, while inductive or capacitive loads may cause it to fall below 1. Now, let's focus on the inner workings of a transformer. Internally, a transformer encounters two main types of energy losses: copper losses and core losses. These losses are critical when determining a transformer's safe operating capacity and form the basis of the kVA rating. Copper losses, or I superscript 2R losses, occur due to the resistance in the transformer's windings. As current flows through the copper coils, heat is generated. The higher the current, the greater the heat produced. These losses depend solely on current, not on the power factor. For example, a transformer delivering 100 amps will have the same copper losses whether the load has a power factor of 0.8 or 0.5. Core losses, also called iron losses, arise from the alternating magnetic field in the transformer's core. These losses are caused by hysteresis and eddy currents and depend primarily on the voltage and frequency applied to the core, again, not on the load's power factor. Core losses remain nearly constant regardless of how much load is connected. With these principles in mind, transformer designers must ensure that the transformer can handle expected voltages and currents without overheating. The temperature rise within a transformer, driven by both copper and core losses, determines its capacity. Since these losses depend on voltage and current and not on the power factor, transformer ratings need to reflect this directly. This is where the significance of the kVA rating becomes evident. Power factor is a variable determined by the user's load characteristics, and manufacturers cannot predict or control it. If transformers were rated in kW, then their usable capacity would vary with each application, risking confusion or even equipment damage. Consider this example. A 100 kW rated transformer would seem to suggest it can handle 100 kilowatts of load. But if the connected load has a power factor of 0.8, the actual apparent power becomes 125 kVA. This mismatch could overload the transformer, since its heating limits might only accommodate 100 kVA. By using kVA ratings, transformer manufacturers provide a consistent, universal measure of capacity. It ensures users know the maximum voltage current combination the transformer can handle without exceeding safe temperature limits. Users can then determine their allowed kW output by factoring in their load's power factor, ensuring compatibility and safety. In summary, rating transformers in kVA avoids assumptions about the load's power factor and focuses instead on the actual physical limits of the device voltage and current. This method ensures reliability, safety, and efficiency across a wide range of applications. Ultimately, the kVA rating is a practical engineering solution that accounts for all possible load scenarios, offering flexibility and consistency in transformer use, regardless of the electrical characteristics of the connected equipment.